Hello, everybody. Welcome to Square Pegs and Possibility. Here we are on lesson number 3, pipeline analysis, which is part of the series, which is the course Closed Conduit Pressure Flow. And the purpose of this is to prepare you to take your civil PE exam. This lesson will cover both AM portions and PM portions. So there'll be some topics that would be found in the water resources environmental PM portion as well, and we'll call those out as separate items, so you can tune out if you don't need those. That being said, we'll jump right in. It's broken into parts, and we'll start with part 1 here, single pipes. This is an add-on from the lesson number 2, and it's based off the Darcy-Weisbach equation for friction loss. We can represent that equation as a function of flow as opposed to a function of velocity. We did that in an example problem, and we had some numbers there, so we were able to turn these variables into real numbers. But yes, we can change this as a function into a function of a flow as opposed to a function of velocity. And essentially, if we isolate everything from the Q and call it K, then what we have is a very generalized format of the equation KQ squared. Likewise, if we do such a thing with the Darcy-Weisbach, we'll have this 185 carry over to the Q, and we can take all this other business and call it a K. So a generalized function form for friction loss is essentially KQ to the N, where N is 2 for Darcy-Weisbach and 1.85 for Hayes and Williams. I don't have an example problem specific to that at the moment, but this is going to be very important for us as we move forward in more complicated analyses of pipes and pipe systems. Okay, moving along. So let's first look at pipes in series, part 2 of this lesson. What are we talking about here? Well, we're talking about pipes that are connected, that are different from one another across the length. That means they are in series. So we have a pipe with a diameter 1, diameter 2, diameter 3. They all have varying lengths, and they all produce different friction loss with the same flow that goes through. So the Q, or Qn, is equal to Q1, which is equal to Q2, Q3, etc., where the friction loss is equal to the sum of all friction losses experienced across the total amount of pipes in series. Well, we know from the last page in that we were just on that we can take H sub F and turn it into a KQ. So H sub F1, K1, Qn, K2, Qn, K3, Qn, you add them all together, and you get H of F, or that can be substituted for an equivalent K, Q raised to the N. The equivalent could be, K1, K2, K3 all together now. This is a bit confusing maybe, but essentially what you really need to walk away with from a conceptual point of view is the Q is the same throughout, and the friction loss is added up across the length. Converting all this into K, Q to the N, etc., that we'll learn how to do a little bit more when we work out some example problems. There'll be some example problems throughout this lesson, and there will be lots of them in the final comprehensive test that we provide when we get to that point. Okay? So we're going to jump into one example. It's going to throw a left curve at you. It's the point of our examples is to either add on to the notes, by way of highlighting something that was taught in the notes, or add on to the notes by way of throwing you a curveball. So this one's kind of a curveball. Why? Because you'll find out. 3 pipes, all with a C value of 120, so we know we're looking at Hayes and Williams, are connected in series as shown below. Determine the length of an 8-inch equivalent pipe given the provided pipe diagram. All right, so we have 8-inch diameter, 6-inch diameter, 10-inch diameter, total feet, amount of feet per each. That's a pipes in series system. We have this diagram here, which shows at varying diameters, we have head loss amount represented in feet per foot of pipe at that diameter. And we have varying discharges and velocities. So if we had a 36-inch diameter pipe at a 100 cubic foot per second discharge, we can drop it down here to figure out what the unit head loss foot per foot is. Okay, does that make sense? Perfect. So we're going to use these two images to solve the problem. So let's see what that's all about. All right, so there's no flow rate in this one, and sometimes you have to suggest a flow rate or guess a flow rate in order to get things done, and this is one of those times. So I'm going to guess a 1 CFS flow rate because 1 makes the math easier. Next, using the pipe diagram with that flow rate and the diameters of 8-inch, 6-inch, and 10-inch, I'm going to solve for the unit friction loss on a foot-per-foot basis. So the H of F 8-inch is going to be equal to this number here from that diagram, foot per foot. The H sub F 6-inch at that flow rate is equal to this here, and the H of F 10-inch is equal to this here. Okay? If you take all these, we can convert the 6-inch and the 10-inch pipes to an equivalent 8-inch pipe simply by multiplying the total length of pipe times its unit loss, friction loss, and dividing it by the 8-inch unit friction loss, right? So the equivalent for 8-inch for the total system is going to be simply the length of the 8-inch plus the length equivalent of the 6-inch plus the length equivalent of the 10-inch. If we do the math, we're talking about 1,200 plus 1,000 feet times 0.019 foot per foot. And we will make that an equivalent value by dividing it by 0.00475. We will also do the same thing for the 10-inch run. And again, divide it by the 8-inch unit loss. And we plug and chug that value. It becomes 5,979 feet of equivalent 8-inch pipe. And that is our answer. Okay, so not intuitive, not highlighted explicitly in notation in this lesson, however, highlighted in this example. So pencil that in to your notes here, have it available. It can creep up on you on the exam or something like it. Moving on to the next problem. For the 3 pipes in the above image, determine the diameter of a 4,200 foot long equivalent pipe. Okay, so we know that C is equal to 120. And we said that Q is equal to 1 CFS. We're gonna keep with that. Well, I bet if we can solve for the diameter, if we use the Hazen-Williams equation, and already have a value for the friction loss, we can solve the friction loss up hand, plug it into the Hazen-Williams equation, and back calculate for the diameter. That makes sense. You have to be able to see these things. Granted, I wrote the problems, and I'm making it seem like I saw it immediately. It's not all that intuitive, but these are the types of things you have to be able to determine and kind of work with on the exam. You have 6 minutes on average, and you're going to need more than that for some questions. Something like this should only take you a few minutes because there's not many steps. Part of it is realizing what you need to do when you first look at the equation. Okay, so the total friction loss of the system is going to be equal to each run's total length times its unit loss value, right? So we can go 1,000 times 0.00475 0.0195 plus 2016. So the H of F for the total system is going to be equal to 28.4 foot. Good news, because we can take that value and plug it into the Hazen-Williams equation. Right? We can simply plug that in. 4,200 feet. We don't know what D is. We're going to be solving for that with our HP35S solver function, or solving function on the calculator. We assumed 120 to the 1.85, and remember that this all equals 28.4 feet. Therefore, D is equal to 0.6225 foot, or 7.5 inches. And that is the answer. Okay, so again, this was a different way of getting a question around equivalent lengths for a series of pipes on the exam. Both of these would, in my opinion, be considered AM portion questions, but easily could spill over into the PM portion as well. So these are the types of things that you should be expecting to see. Moving on to part 3, pipes in parallel. Just like a pipe system in series, the pipe, instead of changing diameter across its length, could simply break out into different parallel pipes. So the Q coming in is the Q coming into the system via continuity is the Q coming out of the system, but we could assume that this would constitute a junction right here, and this would constitute a junction right here. And in between this junction and that junction, the sum of these three flows would be equal to the Q in and the Q out. The question becomes, what is the Q going into each one of these? What is the friction loss experienced in each one of these? What's the diameter in each one of these? Henceforth, the velocity and things of that nature. There's a lot of questions about how this works out, and there's many interesting examples. We'll cover a few here, but we'll have plenty more to do when we get to the comprehensive exam. So the key here is that Q is equal to Q1 plus Q2 plus Q3, which equals Q out. The friction loss at any given pipe leg is the same as each other. So the friction loss across the system is equal to the friction loss of each leg. Just remember that. Don't worry about the theory right now. If you want to get into the theory, take your time and enjoy that. Pick up some books, read through it. The friction loss across the system is the friction loss, that number is equal to the friction loss head in each, or the friction head in each. Likewise, we can do a K equivalent at Q to the N, right? In this case, they are going to equal one another and the system's value. In order to get the K equivalent, you can raise it to the 1 over the N for each one of them, adding them together. That is the way that this relationship works in solving for the KEs and the Ks. But these are the two conceptual items that you really need to know: how flow is related and how friction head is related between the system and each of its respective legs. So let's go into example number 3. For the system below, the pressure head at A is 120 foot of water, and the pressure head at E is 72 foot of water. Assuming the pipes are in the horizontal plane, what are the flows in each branch of the loop? Okay, so is this a complicated problem? There's way more complicated problems. There's problems that are going to take a lot more time, but this is something that can pop up on either AM or PM. I'll tell you that now. We do see C values in this problem, so we know we're going to be using Hazen-Williams. We're learning that there's pressure involved, so I'm thinking the Bernoulli equation as well, right? This is where my mind is working. So let's take a look at the energy equation, right? At A and E. So let's go ahead and write them down. We know what this is, but you have to write them down. Velocity head, potential head equals the pressure head at E plus the velocity head at E plus the elevation head at E plus the friction loss. Well, the problem said horizontal plane. That means we don't have any delta in the height, correct? So what can we do there? We can say that the z's are zeros, okay? And between A and E, we're assuming, because we haven't been told otherwise, that the diameter is the same. If the diameter is the same, then the velocity heads cancel one another out. So that provides us with a very easy equation to look at. 120 plus 0 equals 72 plus 0 plus h of f, which means that h sub f is equal to 48 foot. So that's across the system, but it's also across each one of the pipe legs that are in parallel. So all we have to do now is take that h sub f, and plug it into the Hayes-Williams equation. We know the C values, right? The C values were given to us as 100 for each. We know the C values. So if you take the Hayes-Williams equation, Q equals 0.432 C D to the 2.63 S to the 0.54, where S is equal to h of f over L. Remember that slope. Then we have everything that we need to solve for Q. Therefore, QB is going to be equal to 2.2 CFS. This is now plug and chug at this point. QC is going to be equal to 1.4 CFS, and QD is going to equal to 1.7 CFS. And those are our answers. Okay? So, what did I do with this? I simply took that value of S and brought that fraction h of f to L. Remember, h of f is 48 feet for each one of the legs of run in that system. So that remains constant. And then you just sub in the L value, the C value, and the D value for each and plug and chug to get these numbers. Interesting problem, type of thing that they would throw you on the exam, try to stump you. Example number 4, from the diagram below, which of the parallel branches will carry the most flow? We don't know the Q in, we don't know the Q out, we don't know the Q in either branch, so we know we need to equate the values or the formulae of both of these branches so that we can then figure out which one has the possibility to carry much more flow. Okay, so if we're going to equate these two branches, we can start by saying that we know that the friction head of A is equal to the friction head of B. And if we do that, we can say that then the V raised to the 1.85 times L divided by C, 1.85, 1.165, and is going to be equal to the same thing over on the B side of the equation, and this is, a Hazen-Williams relationship. However, we don't have any change in diameter. The diameters are the same in both of these branches, so we can get rid of these. Let's just make our lives a little bit easier. The C values are different, so we can't do that. What about the lengths? Can we do something with the lengths? No, because the lengths are different too. And, velocities are key to kind of getting to Q. So what are we going to do here? We're going to say that VA to the 1.85 times 1,000 foot divided by 130 to the 1.85 is going to equal VB to the 1.85 times 500 feet divided by 100 to the 1.85. And we could take all of that and we can say that 0.123 VA to the 1.85 is equal to 0.100 VB to the 1.85. Now, in order for these two things for these two formulas or these to be equal, for the equality to hold true, then VB must be greater than VA. And if V is equal to Q over A, but there's no change in diameter, then QB must be greater than QA. From the diagram below, which of the parallel branches will carry most of the flow? B. Leg B will carry most of the flow. So it makes you think that you're doing simply a qualitative type of question here, but in order to get to a qualitative answer, you have to perform some math and compare these two sets of formulae, and once you do that, then you can figure out which one has the capacity for more flow. Trick question. Could you see this on the AM? Certainly. Could you see it on the PM? Certainly as well. So things to look out for, okay? Moving on to part 4. Now this is PM specific. Pipe networks are called out only on the PM. After this, though, if you want to fast forward, we do have the branching reservoirs. You typically see a complicated branching reservoir question on the PM portion, but a simplified version in some way, shape, or form, qualitatively or quantitatively, could potentially fall in the AM portion. People can dream up all types of things. So you might want to fast forward a little bit to that section just to see how it works, to get a concept and at least know where in your notes you can go to look at things. There are some qualitative questions that could be presented for sure with regards to that. But pipe networks is explicitly mentioned as a PM component of the civil exam for water resources environmental discipline. That being said, you should only spend your time on this if you believe that you must. So pipe networks are interconnected forming, are pipes interconnected forming a complex loop configuration. They look like this right over here, right? Or something like it. You basically have flow in, it splits in different directions. It might run in circular patterns, and it makes its way out from different places. That's essentially a pipe network. There's two important principles to remember when analyzing pipe networks using the Hardy-Cross method. And the Hardy-Cross method is the method that you would be using on the exam to do this if asked to. One is at each junction, the total inflow is equal to the total outflow. That's good old-fashioned continuity. So the pipe flow that comes into this junction is going to be equal to the sum of the outflow coming out. You have to add up these two to equal that. We're not having any loss at the junction. So that's continuity. That is simple. And the second is the algebraic sum of the head losses, or the friction losses. We wouldn't have pipe fittings end friction losses to consider in a pipe loop on the exam. So the algebraic sum of head losses around any closed loop is equal to 0. That's more to bother you on the exam with some sort of qualitative question. To solve these problems, we just simply apply a methodology. And we're going to show the methodology here, so you can just simply apply it and then you're done. You don't have to really worry about much of this, but that is what it is. You'll have to determine from the exam if you're going to analyze with the Hayes-Williams approach or the Darcy-Weisbach approach, because you'll be given either a friction factor or a C value. And then, depending on what your units you're going to use, I'm guessing either one of these two or one of these two, you would use these values to determine the value of K. Remember those Ks? And then we would take that K, all that mess, and we would we'd multiply it against some sort of Q to the N, where N equals 2, N equals 2 for Darcy-Weisbach, or equals 1.85 for Hayes-Williams. So it's just worth, making note of that, because this is, like I said before, is going to come into play when we get into these more complex systems. With this information, the Hardy-Cross method procedure is follows. It's simple. It's really, you can make more errors in your methodology by not being, really detailed. So the point is to be very detailed when you do this. But first and foremost, you have to assume directions and values for Q in each pipe of the network, satisfying that inflow is equal to outflow at every junction, as well as the system overall. So, for example, if the flow's coming in over here, we can make an assumption that the flow goes this way and the flow goes this way, and that, part of this is 2 CFS and part of this is 2.37 CFS, right? Because that value and that the top two branches added together are 4.37 CFS. So this this item number 1 says assume directions and values for Q in each pipe. Okay, so that would be the first part. Next, you compute the friction losses in each pipe from the Q values that you assumed and the K values in which you calculate. And again, the K values are going to be calculated from this table. You'll have a diameter of the pipe, a length of the pipe, and either a C value or a friction factor value from the question. Therefore, you can calculate K values and Q values, and from the K and the Q, again, K, Q to the N, you're going to have a friction loss in representative of feet, or H sub F. Once you have the H sub F, you're going to be able to put that, you're going to have to carry that into a correction factor. The correction factor is applied to each of your estimated flow rates. So you estimated some flow rates up front, you got it all the way to solving for a friction loss in each pipe, and then you take that friction loss, that H sub F, and you create a delta that you apply to your original flow rate. Okay? And you'll see the methodology play out and how simple this becomes. And you do that by saying, by applying this, this is how you get to that correction factor. It's a negative sum of the H sub F's for each loop. And you take the n, the 2 or the 1.85, and times it by multiply it again with the sum of the absolute value of H of F over each Q. Okay? And then when you have that, you apply it to your original Qs, and you go back in and do another iteration. Again, solving for the friction loss, again solving for the correction factor, and again and again and again until you have negligible difference in your flow rates after applying correction factor. So when the correction factor gets really, really small. So what they'll do on the exam is they'll probably make estimates for you on direction and flow rate. So you only have to do 2 iterations or 1 iteration to develop the correction factor and apply it to the flow rates. making your life easy. If you have to estimate your own flow rates and directions, then there's no telling how many iterations you have to do. But if the directions and flow rates are already estimated for you, then you're in good shape. So that being said, let's take a look at how one of these problems plays out. Example number 5. Now I'm going to do it a little bit differently than we normally do it. This way it's very legible, and you can take notes, and then when we have real example problems in the comprehensive exam, you'll be able to apply your methodology very easily. Okay, so the C is equal to 120 for all of the lines, so we know we're going to use we're going to get the K value by using an N of 1.85, and one of the formulae one of the formulas in the table that we had a few pages up in front of this. So we are going to provide to you, as I suggested, maybe what you would see in an exam, that we are going to assume what the directions are and the flow rates are for the first iteration. So came in, it got broken into 2. And we've made estimates and made direction choices for each. The direction choice is very important because it helps you get to positive or negative numbers. And I'll show you why. For each loop, you have to make an assumption that the basis to perform your analysis for positive and negative numbers, just trust me on this, is going to be from a clockwise look or a counterclockwise look. I say just go with clockwise, make your life easy. Therefore, every time you have a flow that's with it, so if this goes clockwise, the 0.5 is going down with it. It's with it, that's a positive Q, but it's against it here, so it's a negative 2.37, it's a positive 2. It's a positive 0.5, it's a negative 2.37. In this case, you have a positive 0.73, you have a negative 2.38, you have a negative 0.5, you have a positive 1.15 from a flow basis. You would apply the same, you would apply the same to the friction loss as well, and you'll see what I mean. So step 2, after you've done that, step 2 is compute the friction losses for each pipe using the information from the equivalent resistance tables, which we provided. So K is going to be this formula for, CFS flow rates. So 4.72, take the length, we have it, take the D, we have it, take the C, we have it, and K is 0.67. If you take that 0.67, you multiply it by the flow rate, raise it to the 1.85 because it is a Hazen-Williams approach, you get a positive 2.42. Positive 2.42. It's not negative. So where did we get the 2 on the flow rate? We looked at this branch right here, and this is the example branch. Why is it positive? It's positive because when we circle around that way, it is the same direction. It's the clockwise direction in the loop, so it would be positive. Even though this number is always going to be positive because K will be positive, and this number well, potentially when it's squared will always be positive. We're going to stick a positive or negative number here based on that flow value there, okay? It's just the way that the problems work out. The 2.4 value is positive because we chose to analyze the loops from the clockwise basis. If the pipe's flow is equal to the direction of your basis, the friction loss value is positive. Otherwise, it's negative. Performing this process for the following pipes in the network yields the following. So on a loop 1, and we have loop 2, let's call that. In loop 1, we have A to B, B to C, C to A. A to B, B to C, C to A. Calculate the Ks the same way. So what changes? The length changes, the diameter changes. The C value is the same for all. So you get the K values, okay? Then you go over to the Q value. Determine if the Q is positive. We got positive, positive, negative, right? We got positive, positive, negative, negative, right? You can see them right here. Then you go into the H values. You solve it the same way. And you have positive, positive, negative, positive, positive, negative, negative. If you sum them up, you get the number below the bottom line. Remember, we're going to need the sum of the f's for the numerator of the correction factor value of delta. So that's the first part of the methodology. Then, for the second part of the methodology, you take the absolute value of your h of f, right here, this value, and divide it by your q. So that divided by that absolute value, they should all be positive. Then you sum them up because you're going to need them in the denominator portion of your correction factor. So you sum all these up. I would say calc all these right now. Make sure you know what you're doing. All right, so taking this equation for loop number 1, the sum of the h of f's is right here. The n is always going to be 1.85. The sum of the absolute values is here and here. Negative and negative is positive. Negative and positive is positive. Excuse me, is negative. But since it's 0, it's 0. That's a brief mistake here, but that could just be 0 without the negative. Okay. So then what do we do? Well, it's time to apply these correction factors to the original assumed flow rates. All right, that's what they're there for. So this would essentially be where the problem stops. It would say either calculate the correction factor, or by, given, if the problem gave you the estimates for flow rate and their directions, they would say, please tell us what after one iteration, what the flow in pipe AB is, something along those lines. So you get the correction factor and you have it, and you go over to the Q and you add it. So if the original Q was 2, you add 0.02 and you have 0.02. The original Q was 5, you add it. 0.37 is negative, plus a 0.02 is negative 0.235. See how they relate? Same thing, 0. These should all be the same because we were adding 0. Now pay special attention to loops for this loop right here. This is interesting because if pipe run BC is impacted by both loops. So we would be looking at a correction factor that is negative, okay, from a CB analysis, because it goes against the flow rate, and we're looking at one that's positive from a BC analysis. So if we look closely at that, even though I did make one mistake in saying that these would all be the same. They're not all the same because we have to apply the loop 1 the loop 1 correction factor in the run CB, but because they're opposite in direction, it's negative. So negative 0.5 plus a negative version of this correction factor is negative 0.02. When you add the two of them together, you get a negative 0.52. So the key is adding them both in those circumstances, okay? So taking a closer look at pipe runs BC, you take the Q and you add the delta loop from 1, delta loop from 2. In this case, it's 0.5 plus 0.2 minus 0, minus because it's the opposite direction. In this case, negative 5.2, negative 0.2 plus 0, opposite direction. And those are the values that ended up in the table on the previous slide. So in theory, if you needed to do this over and over again, you'd do another iteration, and you would start that next iteration with these new flow rates. Okay, so essentially the side over here would come over here and become your original flows. All right, and you can see that here. And then again, you would take those flows with your K values to determine your H sub F's and your absolute values, and you would plug those into your delta equations for each loop and apply them to these. These would be your now basis flows. So you'd apply your correction factors to these new flows, not your original flows. And when the difference is negligible, you know you've gotten to the end. Okay? But on the exam, they'll ask you to do one iteration and apply the correction factor to a pipe run, and maybe ask you for the direction. So that is the scope of work for these types of questions. This is definitely a PM, and we'll go through a couple of these for sure on the comprehensive exam. So be prepared for those. Moving on, the branching pipes is a problem that shows up in PM definitely, and could show up in a very simple form. The concept can be challenged or tested in the AM portion. But a branching system is essentially you have a reservoir feeding two with some sort of junction in between. Okay, and we're not looking at it with a pump. When we get to pumps, which will be another lesson in this series, we'll look at this with pumps in between the reservoirs. But right now we're looking at head getting the work done. So in a branching pipe system, flow from a single reservoir branches off into two or more reservoirs. How the flow is distributed among the reservoirs depends on the reservoir's elevation heads, and therefore for each branched reservoir problem, energy balance equations must be used to analyze. So we're going to be using energy balance equations to figure things out. Additionally, velocity head can be considered negligible compared to elevation and pressure heads, so we can get rid of those when we do the energy balance, and therefore can be considered equal to zero in branch reservoir problems. Also, minor losses can also be considered equal to zero unless otherwise stated in the problem. So you could have in a PM portion a pump and several valves and entrance and exit losses, friction loss to calculate, minor losses to calculate, and pumps to add to the equation. But really, you're still working from a Bernoulli equation, an energy balance equation, to figure these problems out. And typically, you're solving, you're generating three energy balance equations and using them as a group of formulas to solve for one common variable. Okay. All right. So why don't we jump into an example using that picture? Using the previous branch reservoir image, from reservoir A, the water is supplied by a pipe that is 24 inches in diameter and 2,000 foot in length. Pipe run DB is 3,000 feet of 18-inch pipe, and pipe run DC is 1,500 foot of 15-inch pipe. So we have lengths of pipe, we have diameters of pipe. The surface elevations of A, B, C, and D, the junction, are 170, 50, and 80 foot respectively. What is the flow in each pipe if the friction factor for all pipes is 0.007? So they give us the friction factor. We know if we do an energy balance equation, H sub F is going to be involved. And to get to the H sub F, given a friction factor, we're going to use the Darcy-Weisbach. We know that. So to make life simple on this problem, this is the energy balance. We have pressure, velocity, and elevation heads plus the H sub F. Pressure heads at, and we're gonna analyze this at points AD. We're gonna analyze this at points DB, and we're gonna analyze this at points DC. And we're gonna have three equations to consider. Okay, so if we're doing this from points AD, 0, 0 elevation. Then we have a pressure at D because it's not exposed. That's the junction. We don't have velocity there. It's negligible, remember. We do have a D height, and we have a friction loss. So if we rearrange these and we sub out for H of F, KQ squared, remember squared because it's Darcy-Weisbach. If we had a C value, that would be a 1.85. Remember, using the generalized function form is very helpful when we're doing these types of equations. All right? Don't get caught up in all the math if you don't have to. So this is H sub F, and if we solve for it, we have height at A, pressure head minus pressure head at D minus the height at D. That is equal to that. If we do the same thing for between points D and B, will yield a very similar equation. I recommend you crunch those out as well. And if you do the same things between D and C, we'll derive a very similar equation. And what we find is for each one of these equations, we have K's that are unknown, Q's that are unknown, and pressures that are unknown. But from the continuity equation, we know that QAD, what's flowing out of reservoir A on the left and making its way to the junction, is going to be equal to what leaves the junction in both of those pipes together. Continuity at the junction. We're not having any loss at the junction. So QAD is equal to QDB plus QDC. That is key because now we can relate these three equations, right? The three energy balance equations have two unknowns. We talked about this, Q and K values. So we can solve for K. We have the F, right? And we have the L. They gave it to us for a reason. And we have the diameters. So we can solve for each of the K values. We can bring those back to the original equations. And if we take the K value 1, 2, and 3, and put them into 1, 2, and 3 of the equations from the previous page, we're left with having Q as a function of the pressure or pressure head at point D. Correct? But if we take these new equations and use the continuity equation of QAD equals QDB and QDC, then we can say that this value is equal to this value plus this value. And if we do that, we have essentially an equation that is a function of PD or the pressure head only. And if we look at solving it from the pressure head perspective, the answer is 10.4 foot. We can then take that pressure head value and go back into each one of the equations for Q, stick it in, and have solved for Q. Series of linear equations. You'll have to perform those most likely in some way, shape, or form in the PM portion of your exam. And that's how you solve a branched reservoir problem. You don't solve a branched reservoir problem by having a simple formula that you pull or a set of formulae that you pull from. You literally need to look at each one, and you have to do an energy balance from each reservoir to the junction, set up a series of linear equations, and solve for what they're asking for. That's the approach all of the time, but you never know what you're going to have. You can have one reservoir on the left, you can have one on the right, 3 on the left. You don't know which ones are going to be higher than the other, what the elevations are going to be, where you're going to draw your datum. So that's really the overarching path to take when you have a problem like that. So we've gotten to the end of this lesson. This is the pipeline analysis lesson. This is got some complicated stuff. We went over some sample problems. There's going to be quite a bit more on the comprehensive exam. We're going to have several easy ones, several very difficult ones. We're going to mix them in and out, and you're really going to leave on the opposite end very happy with the experience. So that being said, the lesson is complete. We hope you have found some value here. Please tell everyone that you know and care about this project, Square Pegs and Possibility. We're just getting started. It's going to be many different things, and we really believe that this is going to be great for everyone. So please share the information with everybody that you can, that it's here. Let them come over here to register or sign up or take the courses. And best of luck on the exam, and tune in for the next lessons and for that final comprehensive exam. Best of luck. See you soon.